Bonjour, je me présente donc Anik Mandalian.
I'm Anik Mandalian. I'm an associate architect at Provencher Roy Architects, and I'm going to be jointly presenting with Mr. Samir Nafa, who is one of my dear colleagues, who is BIM coordinator at Pomerleau, and who is working on the project 100%. I'd like to tell you about a project that's absolutely unique and fascinating. You know that Paris has its Eiffel Tower, Pisa has its Leaning Tower, and Montreal has its Olympic Stadium with the highest inclined tower in the world, 165 meters high. It's an emblematic icon of Montreal, and I'd like to begin by presenting the context of the project to you, and then tell you about the BIM project in the collaborative mode. I'd like to then join with Samir and tell you about the challenges that we had to deal with throughout our project. There are several of them, but we'll present 4 to you. We chose 4, and they were largely resolved through the BIM process. In closing, I'll show you a video made by the Olympic Park on the hidden structure of the Montreal Tower. In 1976, the Olympic Stadium was built for the Olympic Games, as you know. But because of structural challenges, the tower was only completed 11 years later, in 1987. It's quite a fascinating structure because it's entirely concrete for the 2/3, and the top third is in steel because, again, there were structural constraints in terms of the weight. So we have steel at the top for the top third.
A toujours été dédié.
And the tower was always supposed to support the retractable canvas roof. Roger Taillibert's initial intentions, he was the architect, was to try and unite all the buildings. In other words, on the whole site, there was the stadium, the site, and the tower. They were all for sports. And the Olympic Park announced, well, for the last 30 years, the tower was never used. It wasn't occupied, that is to say. As you see here, this is the inside of the tower. There are no columns. It's a concrete structure with basically blind walls with prefabricated panels and windows on top to control the amount of natural light that was going to flow in, because the architect thought that this was going to be for sports. So there would be basketball and badminton courts and basketball hoops and gyms. So it's quite fascinating because the function is completely different now, 30 years later. The tower was never occupied, and the Olympic Park is announcing that it's going to be using the tower by in order for Desjardins Financial Group to use it, starting in 2018. So let's briefly describe our mandate. We were mandated after a public call for tenders in 2015 to work on many projects, the renovation and reuse of the Montreal Tower. Essentially, it was a basic building, and we had to redo the envelope. As I mentioned, the sports vocation of the original building has now been changed, and it's going to become office space. So the client mandate was to integrate a curtain wall so as to have more natural light come inside the workspaces, so that there would be quality workspaces. The Desjardins offices would be for over 1,000 employees to go through the tower, work there, and they're open areas with very few walls separating them. So we had to work, we wanted to conserve the initial form and the initial look of the tower. Now moving on to BIM. One of the essential processes for one of the essential aspects of BIM is collaboration, as we all know. So we had the Olympic Installations Board, who was our client, and they supported us in our use of the BIM process. Why? Well, for several reasons. Obviously, the idea of working what's existing, the forms were highly complex. The scheduling was quite tight because the contract was awarded in May of 2015, and the curtain wall is to be built in a few months, in September 2017. The project is being done in building management with Provencher. The structural engineers are a Denver company, and then BPA for the mechanical electricity. So we have a series of teams working together to complete the project. Obviously, it's a quality project, and we have to work in collaboration with each other. So one of the first things that we had to determine right from the beginning was to have collaborative meetings with the client. We needed to have design meetings with the model. We had management meetings. And then in building mode, we had meetings with the subcontractors. They were key subcontractors, such as the curtain wall contractor. This was one of the key factors in the entire production of the project. The BIM challenge involved working in collaboration. Obviously, we had to work with construction managers and subcontractors and professionals. Everyone had to work together. We used 3D modeling with specialized contractors, and I'll tell you more about that later. And we used mobile technology, of course, on the building site. And all the follow-up changes, modifications, and amendments based on how work was progressing, all of this was done on a daily basis. We use tools such as Enscape, L'Union, Revit for the design. We also use BIM Glue for coordination, BIM Field for efficiency. I mean, you could just imagine if you have problems and shortcomings, you've got your professionals who are in a crane. You can't imagine having papers all around them when they're up in a crane and you're suspended hundreds of feet above the ground. Now I'm going to let my colleague Samir tell you about the collaborative mode in lean construction. Thanks, Anik. I think having the designer, architect, and representative of the contractor side by side is a really good example of collaborative work. I'd like to tell you about lean, which is another tool used by Provencher. And it, again, depends on collaboration, as other presenters have referred to. Lean is just a management system which optimizes any work process on a work site and tries to eliminate waste. There's also a last planner system. So if you look at the photo on the left, you'll see there's a big chart on the wall. That is planning for the next 3 to 4 weeks. And then there are various post-it notes. Every color is a different contractor. So on the right, what you see is a meeting where you have all the different contractors, and we do this twice a week. And what's magical about the system is that planning doesn't go according to this traditional system where you impose a contractor, you impose dates on the contractor, and you have, let's say, a project manager impose the date on him. No, the person who's doing the work is in the best position to know how long it's going to take. And then he has to respect his commitments, of course. So you have everybody together, and they plan together, collaborate with each other to find the best possible way of planning. And what's magic about it is that it's visual as a tool. So you get a general overview of the planning. Again, it's based on the collaborative model. From my personal experience as a coordinator of different contractors, I can tell you that you're better dealing with someone who's not so great in BIM but who has a fantastic mindset for communications and collaboration than someone who's the Einstein of BIM but who doesn't know how to collaborate or communicate. That's my personal experience. It's really important to have that spirit of cooperation, coordination, and communication. And now back over to Anik. Well, now let's look at the challenges. from challenges to reality. So this is a video of the cloud points, the cloud data, the data cloud rather, to give you an idea of just how big the project was. So we started to work on the design model, and we used data clouds. We had them for outside and inside. We have the outside one, and that essentially covered the whole portion of the tower.
C'est sensiblement 40 000 mètres carrés, donc c'est assez.
In every stage, we had a data cloud generated. Now, as you know, there is no junction between the inside of the tower and the outside. So it was two separate phases. You had to first demolish the prefabricated concrete panels for the installation of the curtain wall. You had to make a link between the two. So why data clouds? And you have such complex volumetric data here. So the inclined tower, you could barely see this, but there's a torsion and a curve to it. So the existing plans, the plans for the existing model were not very reliable. There were several versions of these plans, and the architectural complexity was great. So a data cloud was absolutely essential. Here you have an image of the data clouds and how they're transformed into a rivet model. We realized that for the outside model, sometimes there was shading. The data cloud wasn't accurate. So when we modeled certain gutter portions, they were used to drain rainwater, but we had accuracy problems, so we had to revalidate all the information. So, and now I'm going to turn this over to Samir, because when we worked on the design model, we transferred the design model to the contractor so that it could become a build model, so that subcontractors could integrate their work. We did our interdisciplinary coordination between mechanical, electrical, structural, and architecture, and then we were transferring it for construction over to the contractor. Thanks, Anik. I just wanted to add that between the design and build phases, the model switched from the designer to the contractor. But you have to audit the design model first to be sure that there are no errors. There could be human errors or others. Sometimes there could be two columns of concrete on top of each other that would have an impact on estimating the quantities. Or what about phasing? You could have a project where you have a part that's in existence, and a part that's being demolished, and a part that's new construction. You have to make sure that each element is in the right phase. So we had an audit of the models done by a professional to be sure that we were not dragging any design errors into the build portion. And we did find that the professionals had done the models properly. So now the design of the curtain wall. Here there was a challenge because of its very shape. The curtain wall cannot be designed with the curved glass, but the tower had a curve. So we thought of extending the slabs. So for example, if you look at the existing plan, if you look at one of the floors, for example, the slab was actually curved. So we had to straighten the slab so that there could be a parallel relationship for the walls from floor to floor. So the bottom of the curtain wall is at 60 degrees, and every floor saw this angle change by about a degree. So we would never have been able to do this without BIM and without trial and error. So this is one of the complexities that we were able to overcome using these tools. In August of 2016, the cranes were installed on the site, and we could thus demolish the prefab concrete panels and the windows so as to build the curtain wall.
You can just start the video. Okay, thank you. Ensuite,
And then in September, we asked the curtain wall contractor, after a few of the prefab panels were demolished, we asked them to come and scan the whole tower. So this is the Revit model of the built floors with the curtain wall. So in here, you see that they're pre-glazed models. We have the spandrel that, and you also have the channels for the draining. So these are three essential elements. So the curtain wall contractor scanned what was existing in the model, and he told us that he needed to have the scan of what was real for the prefab demolished panels before he could produce any shop design. So we were short of time, so he had to come and scan once. And then we had a meeting in November, which was critical because we were all sitting around a table. There were about 20 of us together, and we were trying to find a solution. So here you see the totality. There are 4 curtain walls, one on the west, one on the east, and 2 on the south face, facing the roof of the stadium. So we found a solution because we realized that the curtain wall contractor had made his model of the curtain wall, and he had inserted it into our model, and it didn't fit. So there was a problem. So there were about 20 of us sitting around a table with the contractors who were doing the demolishing, and we were there with the people who were going to be building the slabs, the contractors who were in charge of the steel structure, and we found and Pomerleau's people, we found a solution together to be able to demolish the prefab panels in an accelerated fashion, working day and night. And those were on the edges so that we could scan, and here you see an idea, you could scan the junction between the existing slab edge and its relationship with the existing channel so that we could have the right data because we didn't have the right ones. So we did this, and 2 weeks later, the curtain wall entrepreneur came back in. The contractor did a new modeling, and the curtain walls fit. So that was quite an exceptional challenge, and we were able to overcome it with the help of BIM tools, and without the BIM, we would not have been able to get past this problem. Another area in which we used BIM on the construction site, I think you can see up here, here's the position of the cranes on the site. As Anik was saying, we were dealing with a rather unusual and extraordinary architectural shape, and BIM was very useful. We had 2 cranes positioned on the site, and we had to study various scenarios to be able to be sure that the location of the cranes was in fact optimum and that they covered as much surface as possible. We analyzed several scenarios and ultimately found the position, which you see here identified on the photographs. Another use of BIM was to be sure that we had effective health and safety management. Some of you came to the site yesterday and you saw the dismantled panels. Thanks to BIM, we were able to look at various scenarios so that we could have a security perimeter in case any of those panels were to fall. Obviously, we used BIM to make sure that traffic moved freely, that delivery of materials was done in appropriate conditions. Here you see crane number 1. Some of you saw it on the site. It's over 200 meters high. It is the tallest crane in Canada right now. And what's unique about it is, as you can see on the image on the left, It spans the existing stadium roof. And in addition, the two Canadian arms, which hold it in place.
Ça a pas l'air très grand comme ça sur une...
You can't really see this on the photograph, but these are, the trusses are over 2 meters high. And this was simplified thanks to the use of BIM.
Autre élément aussi important, c'est le funiculaire.
And then you know that there's a funicular, which is used to bring tourists up and down several times a day. And if you have this tallest crane in Canada and you've got tourists going by it, it's rather a scary thought. So we had to look at several scenarios to be sure that the crane installation was not going to get in the way of the funicular's movements. And it's all working very smoothly, but that was another application of BIM and the 3D model, because it was used, again, to overcome various problems. I'd just like to add something. One good thing about the process was that the funicular modeling helped us to reassure the client, because the funicular is a tourist attraction and which is internationally famous. There are a lot of events at the Olympic Stadium, so this is something that's highly sensitive. We had to be sure that the work site was really secured versus all the events taking place. And this was a fabulous tool to show the client that there was nothing to fear. There wouldn't be any conflict. The location of the crane was not going to hinder the trajectory of the funicular. Here, what you see on the left is shaft number 1. That's what we called it. And this goes all the way up the length of the crane. And what you see that's rectangular and circular in yellow, those are shafts that are over 2 meters wide, 6 or 7 feet wide. So they're rather impressive. Why? Well, because they're big, but also they have to follow the curve. So if you're working with the old system, you'd have to go with your measuring tape, and it would be extremely complex. But here, BIM really was useful. Now, the contractor wasn't comfortable with BIM initially, and we really supported him, and he really progressed all throughout, and now he's one of the best in BIM. So you can deal with contractors who may not feel so comfortable, they may not be so excited to embrace it, but they can really develop, and we're very happy to see this. There were other issues as well related to these shafts and ducts. Yes, there was a lot of coordination. What you see in blue, which is circled in blue, is important because in the big areas, they had steel walkways in them, or they were part of walkways which were there to give access to deformation sensors, because the whole tower is monitored every year. And the client needed to have access to that, because it's essentially normally a closed system. So with mechanical engineers and architects and structural engineers, there was a tremendous amount of coordination required, because it's such a limited space. And we had to almost show the client screenshots of the 3D to have authorization and permission, because at one point there was a duct going through and we needed permission to have only 5 feet to go underneath it to get to the sensor. So this was quite a challenge, and it all went well, very well, I may add. So now we like to show you before and afters whenever we do a BIM presentation. So this was shaft number 1. It's already half the height of the tower, and it's all been going very well. So in closing, I'm going to show you a video made by the Olympic Park, and it's going to give you an idea of the extent of the project, and it's called The Hidden Structure of the Montreal Tower.
I understood that it would work. I saw the schedule that we discussed.
Foule en haut, c'est à toi, François, c'est beau. Vas-y, mon homme.
Attention, on va débarquer.
Oui, monsieur, c'est ça. J'en reste 3 après. OK, on emmène la porte.
Donc, pour conclure,
Now, to conclude, it was obvious for us that the project could have been executed without the BIM process. It's a collaborative project with all of the stakeholders, the client, the construction manager, professionals, subcontractors. We were very lucky to work on such a project, such a big project. For the time being, we're all working to produce a quality product. Thank you very much.